Okay, so we were discussing LTL, satisfiability and model checking, right? Like, so the satisfiability problem was essentially given an LTL formula. We look for the existence of a computation such that the computation satisfies the LTL formula. And in the case of model checking, you were given a system or a model, system model, and then you want to check, and also you were given a formula, you want to check whether the system satisfies the property, and an abstract model for that is, as we discussed, it's the clip case structure, right? And so uh, given such a property phi, what the model checking essentially checks, like the all the executions of the system that should follow the property phi. Essentially, it's a subset of all the words which the executions are essentially a subset of all the words that satisfy the formula phi, right? And the way one would actually do this, check this algorithmically, is like you can consider that this is essentially equivalent to checking that the intersection with the set of words which don't satisfy phi, that should be empty, right? And this is essentially the words corresponding to the negation of the formula. And what if we have a tool to construct an automaton for which the language is the same as the set of words which satisfy the negation of the formula, then essentially what you can do is take the intersection of this briefcase structure as well as the automaton, and then you check whether uh, the language for that is empty. Okay, and we uh, started looking at how to translate such ATL formula into an automaton. And one kind of automaton that we started looking at is like LTL to the translation to alternating bushy word automaton. And we said that the size of the alternating bushy word automaton is linear in the size of the formula. Why? Because we define something called the closure of the formula, and the size of the closure is essentially, what is this? It's like, so given the formula phi, the size of the closure is in terms of, it will be roughly linear in the it's linear in phi. Okay, and why is it linear? I mean, you can think of these like in the form of a tree, and each component will yeah, each node itself, you can, like the topmost node, it may have some operator, or it may be like, if the formula itself is just a proposition, then the entire, like suppose I have like something like P and Q, right? So you have this, and then you have a P and you have the Q, right? So the closure, what will it have? The closure will have P, Q and P and Q. P, Q and P and Q, right? P, Q and the P and Q, right? So you can think of, sorry? Does it have the empty state also? No, it doesn't have the empty thing, right? I mean, the true and the false, for example, like we'll always say, like these are not really states, but there is nothing like an empty. Okay. Yeah. So what here you can see is like P is one node, Q is one node, the entire thing is another node. Okay. So the entire thing, like you can think of this itself as the entire formula. The topmost node here, you can just think of this, the topmost node corresponds to the entire formula. So the number of nodes that you would have is the size of the closure. I mean, you can think of it in that way, and the size of the closure is just like the linear intersection formula, right? So yeah. So and then we saw that like the psi formula itself, because it's in the closure, if there is a conjunction, then psi1 and psi2, similarly for disjunction until release. So these both psi1 and psi2 they are in this. And then if you have x psi 1, then also psi 1 is there in the closure. Okay. X psi 1 is in the closure, then psi 1 is in the closure. So, and we looked at some examples, and we also saw how to construct, for example, like if you have a GFP, like how we constructed the alternative Bushy word automaton corresponding to that. And so this was the alternating Bushy word automaton corresponding to this GFP. GFP is like false release, true until P, right? So what are the, if you consider the closure of this formula, the closure of phi, so what are the things that you would have here? Like true union, no, true until P. So you have true until P, which we call FP. Of course, you also have the full formula, the entire, so that is GFP, and you also have P, right? But as we saw last time, that so the initial state is 1, which has the formula this phi, correct? So the states are all these formulas in the closure. The initial state is the 1, which corresponds to the formula phi. And then what we saw that this P, though it's in the closure, it's not reachable. The corresponding state is not reachable, right? So we just have two states. And also there are a few things like we also defined here in the automaton the transition function, right? So for example, like if um, what is A here? Like so essentially, so this is a letter, and the letter is a subset of the set of atomic propositions. So if you have P is a formula, it's an atomic proposition in the closure. So if P belongs to A, then you have true. Delta of PA is true. And similarly, you have delta of negation of P, comma A, delta of P1 and P2, comma A, and so on and so forth. If you have delta of Xi, comma A, then you go to the state, which is labeled by psi, right? The state psi. And actually, yeah, we should say that you go to the state side, right? Because the state itself is the formula. And similarly, if you have delta phi 1 until phi 2a, then either delta phi 2a or delta phi 1a and phi 1 until. So you have such conjunctions here, and there is a disjunction here. This just comes from the semantics of until. And similarly, from the semantics of release, you have delta of phi 2a and delta of phi 1a or phi 1 release phi 2. Okay, and we also mentioned that we did not formally prove the correctness of the construction, which we will do for another translation from LTL to direct NBW. Okay, and here the set alpha is the set alpha of accepting states. It consists of all formulas in the closure that are of the form phi 1 r phi 2, right? So here, if you see GFP, this itself is of the form phi 1 release phi 2, and hence this particular state that corresponds to phi, that is also an accept state, right, or a gate state. And one of the things, so if we look at all these transitions here, right, so this is the automaton, the ABW, this is how it will look like, right? And one thing we mentioned is that such automaton where the SCCs consist of just a single loop. I mean, SCCs consist of a self loop. So these are called very weak alternating automaton. Okay, and one can indeed show that for such automaton where the uh, the loops are just they or the SCCs just consist of a single state. You have a self loop. There, the alternation can be removed with n times 2 raised to n blow up. In the case of like Miyano Hayashi, where you have alternating like standard ABW, then what was the blow up that we saw? 3 to the 3 to the n, right? Whereas here we are saying that if you have such special kind of alternating automaton, which are called very weak alternating automaton, then the alternation can be removed for n raised to n times 2 raised to n blow up. And indeed, what one can show is that when you are translating an LTL formula to an ABW, what you end up getting is a very weak alternative implementation. Okay, so maybe let's just quickly do for this particular formula. So what about this? Can you now tell me, like, so if the formula is this uh, P and XP until Q, okay? So you recall that what was our the LTL, the kind of LTL formula that we started with, that was in that release PMF, right? Release positive normal form. So that's the kind of that LTL formula we were looking at. Sorry, for translating to ABW. Okay, and why did we introduce the release PMF? Because doesn't give an exponential blow up, as in the case of weak until PNF, right? In the case of, like, if you have so the idea of the PNF is like you want to push the negations inside, like only with respect to the atomic propositions. We started with a standard LTL syntax, and what we try to do is, like, in order to have a PNF, we introduce the weak until formula, but that had that limitation. It's like it blows up the formula, the size of the formula exponentially. Hence, we introduced this release until PNF, where this exponential blow up can be avoided, and we get a release PNF, right? And so when we are translating, so this is all from the release PNF formulas. We are translating this to ABW, and the size of the ABW is again linear in the size of the input formula. And if you are translating that to an NBW, then you get a 3 raised to n blow up for the with the Miyano Hayashi. Or as we said, like, if you get this kind of, I mean, you are getting this very weak alternating automaton, it still gives you like n raised to 2n blow up. Okay. Anyway, so before we get into that, the Vardi-Wolper construction, where we are going from LTL formula to NBW directly, let's do this one example before we proceed. So how do you, so what is the formula corresponding to this? So you have this delta P and XP until Q, right? So this is the formula. And what are my atomic propositions here? P and Q, right? So the letters are, like, you have now the alphabet is, you have uh, like 4 letters in the alphabet, right? So you have P, PQ, you have Q, and you have the empty set, right? So let's do this for each of them. So if you do PQ, then what do you get? So either, so first of all, like, it's a conjunction, correct? So delta of P comma PQ, which is true,
Yeah.
right? And delta of XP until Q,
that is also true.
Delta of XP until Q, comma PQ, right? So this is also true, because here itself you are seeing the Q, and then you see the PQ for this until formula, so this leads to true. Okay, so what about delta of XP until Q, comma P? So what is this? So one thing is, like, so delta of, how are we going to expand it? So if delta of phi 1 until phi 2 comma something, then we check
if phi 1 is satisfied now,
phi 2 is satisfied now. Phi 1
phi
until
2
phi
is
2.
satisfied now, Otherwise, phi 1 has to satisfy and then recursively
Yeah.
the next thing.
So you have this, of course, right? Like, so this is the thing,
Hmm.
or that thing,
Yeah.
right? Or
Delta
delta
xp comma p
xp comma p
uh,
and
and xp until q.
and xp until q and xp until q.
Yeah.
Okay, so this part becomes, of course, false, and delta of xp comma p is p,
Yeah.
right? And xp until q. Clear? So this is false because there is a conjunction here, and delta of p comma q is false.
Yeah.
So you get a false here, and delta of p and xp until q comma p. What is this?
So delta of p comma p is just
True.
True.
And then delta of xp until
So
q
delta
comma
that is like p delta of xp comma p is what? P.
Yeah, so this we have already done here, right?
Yeah, same thing.
So this is this.
Huh.
Correct? So true and this, so you get correct? Okay?
Yeah.
Okay. So now, so you have, so essentially now let's look at the transition. So you have this state. So the only state that we have is this state, which is reachable, right? At least. So you start from this state, and then on P, you are on the same state, right? What is happening on PQ? You are going to true, right? On Q, you are going to false. We did not do one thing, which is like delta of P, and you can check this XP until Q, comma the empty set. What is this? So P empty is false, and XP until Q empty.
That is also.
That is also.
That will go to this p, right?
So
p until.
let's see, delta of no, so P, okay, so it's a conjunction of two things.
Yeah.
It's a conjunction of
So
two
it will
things.
be false.
If one is false, like delta of P comma empty set is false.
Yeah.
So false and anything is false, right? So,
Yeah.
right? So Q and this thing you have, this is false, right? So this is the, so this is essentially the automaton, and you can just try to see how a run here looks like. Okay.
Uh, I have one question. So, the second transition, did we need to compute it? Because once we start from P and XP until Q, we can just reach to these three states, true, false, and P and XP until Q, right? So, do we even need to compute this delta of XP until Q, comma P?
Sorry, I could not understand. Like, why you were saying that I don't need to compute delta of this thing, like
XP until P, yes, because uh, we are never reaching it. Right. So if we start from delta P and XP until Q, with PQ we are going to true, with Q we are going to false, with empty set we are going to false, and with P we are going to P and XP until Q.
yeah. No, I think what is the question?
So it's like in this, we
Uh-huh.
are never reaching the state XP until Q.
Yes.
So like
Yes,
that was the point of computing the transition.
Okay, okay.
yes, yes,
You are right. You are right. Yeah, we are never really reaching this, but
yes.
you are true.
That's it.
You are right that indeed we are not really reaching this particular state. But maybe, yeah, when I was writing, I just started doing this, and then I really, yeah, I mean, yeah,
Okay.
indeed, it's not really required. I mean, you could first just you could have done first this and this and this, and then you could have realized that we are never reaching this, and you need to really come to this. Yeah, I agree. Thanks.
Hmm.
So this is indeed not reachable. So XP until Q is not reachable. Yeah, sure. Thanks. So yeah, you could have avoided the computation. Thanks. Okay. So when you are doing the translation, like so for every translation, one also needs to do the correctness proof, which we did not do in detail. So we are going to do this for the NBW, and this may be a homework or something. Like I'm not going to go over this in full detail, but the idea is of the construction is that like for a formula phi in this closure of psi, like whenever the automaton is in a state phi, then from state phi it accepts all the words in L of phi. It accepts the language L of phi. So that's the idea of the construction invariant that we have, right? And it's indeed true, not very difficult to see for the base case, which is the case for atomic propositions and the negations. And the other cases, they follow from the semantics of LTL and from induction and also from the definition of alpha. Okay.
So, but I still didn't get why the release.
Yeah.
Status.
So you will get some more, it's not very immediate, but you will get some idea when we do the LTL to NBW construction. And then I'm going to give an assignment for the other one correctness. Yeah. But yeah. Right. So yeah, I mean, okay, yeah, let's go over this and then maybe yeah, I'll it might be slightly clear. So the thing is that like whenever even if you are having that release operator, you can think of this like if there is an until condition like phi1 until phi2, that release will also ensure that phi1 until phi2, whenever you see this, eventually you need to see the phi2 DL. Okay. I mean, just by keeping, you cannot just accept by continuing to see only states which are just phi1 until phi2 of the for. Like, so that is the kind of intuition or the semantics of that.
So like eventually we'll go to some true state or something.
Eventually will go to some true state, or eventually, yeah, like, or it will be like you will get to see the phi2.
Okay.
You'll get to see the phi2. Okay, so that's the thing. Okay. Yeah. So essentially, when we'll see this translation from NBW, and we'll go over the correctness of this NBW construction in more detail, then what one would need to do, think in terms of that a computation in that ABW and a computation in that the corresponding NBW, and how that an acceptance condition in this automaton which corresponds to that, which is an NBW, how that acceptance there maps to an acceptance in the ABW. So this is something you need to sort of think about, right? Yeah. Right. So yeah, so now what we are going to do is like, okay, so here what we see is that given whatever we have learned, right, that you can translate an NBW to an alternating automaton, and which also gives like a corollary of that, that you can get an NBW which is exponential in the size of the given formula. In fact, using Miyano Hayashi, we said this is of the size order 3 raised to n. And in particular, we also said that there's a very weak alternating automaton and automaton, and for which the alternation can be alternation can be removed with a blow up n times 2 raised to n. Okay, so this is a paper by Gaston et al. I think just two authors, Gaston and yeah, Odo, something like that. Yeah, so this is I think 2001 possibly. Okay, a CAF paper, most likely, if I recall correctly. Yeah. So yeah, so this paper essentially shows that for very weak alternating intermittent, the alternation can be removed with a blow up of n times 2 raised to n. Okay, now what we are going to do is the other translation, which is very well known. It's a very well known translation, which is called the Vardi-Wolper construction. Okay, it's called the Vardi-Wolper construction, which, given an LTL formula, it directly translates it to an NBW. In fact, what it does is it will construct it, construct a GNBW. Okay, so generalized NBW. Okay, so recall that what a generalized NBW is, that it has some number of some sets of states, right? Of some sets of states. And the idea is that, like, if there are k such sets, then you would like to visit each of them infinitely often. That's the idea, right? Each of them infinitely often. And we also saw that you can translate generalized NBW to an NBW with a polynomial blow up, like k times the state space. Okay, or k plus 1 times the state space. Okay. Now, one thing here is that when we are doing this translation, you can do this for general LTL. You don't really need this to be in positive normal form. Okay, and here the thing is that you can think of, like, at every state of the at every state at every state the automaton satisfies a subset of, or a set of subformula, or a set of subformulas of the given formula. Okay, so so for example, if you suppose there is a word W which is of the form A0, A1, A2, etc., and suppose you have an accepting run for this automaton, and let's call this accepting run to be of this form beta 0, beta 1, beta 2, etc. So the thing is, like, each beta I is a set of subformulas, okay, psi, such that AI would satisfy, sorry, the word starting from AI, the suffix starting from AI, it satisfies psi if and only if psi belongs to beta. Okay, so now the states that we are having, so these are the states. Okay, so these are the states of the automaton. It's actually a collection of a set of such subformulas which are there in the given formula, let's say phi. Okay, so this is the uh, inclusion, and then the you have this run. So the run is the sequence of states, infinite sequence of states, and then we are saying that this suffix starting from AIL plus 1 AI plus 2, it will satisfy psi if and only if psi belongs to this beta I. Okay. Now, just like as we did for the construction from LTL to ABW, we considered the closure, right? Here also we are going to consider closure. So some people would call it an extended closure, let's say ECL, extended closure. But just for simplicity, we would often call this closure. Just the definition is slightly different. Okay. So sometimes we call it extended closure, but I will often will just in this context, when the context is clear, we'll often for simplicity, we'll just call it closure. Okay. So the idea of the closure. So as I say that the formula here does not, the LTL formula does not need to be in PNF, need to be in PNF in this construction. And so the closure here will be all the subformulas that you have, and you also take their negations, right? So we start with, if suppose for example, phi, let's say, is A until not A and B. So here then you have in the closure, you have A, then negation of A because it comes here, then negation of A and B, it's here. So it's like an A phi 1 until phi 2. So you have the phi 1, you have the phi 2, you have the entire phi and everything. And in the conjunction, you have the negation of A and B also you have, just as we saw earlier. And you also take their negations. So you consider here, for example, what is left here, negation of B is not here. So you also add that. Negation of this also you add, and negation of phi also you add, right? Negation of A is already included, correct? So you take these, and now the states are not just individual elements, but these are subsets of such elements. So at every stage, if you are in a state, let's say beta I, then you see that starting, so at this position, the remaining word is going to satisfy all the formulas which occur in beta. Okay, all the formulas which occur in beta. So beta is a set.
One state.
All the
things in that set, the 5 elements are together in one set.
not all of them, not everything in the closure,
Okay.
but a state will be some subset,
Okay.
right? So how is that subset going to be defined? That's what we will see now. Okay, there are certain properties for such subsets that should hold true in order to qualify that as a state. We are not going to consider every possible subset. It has to be in some sense consistent. Like you cannot say that a word is going to satisfy both formula psi as well as negation of psi. It cannot do that, right? It has to be consistent. Okay, so there are certain such properties which these states should have, right? A state is again a subset of the formulas which are appearing in the closure, right? Subset of this set of formulas appearing in the closure or the extended closure. So we'll call it closure only, just for simplicity. So first, right? Yeah, so we just give the definition of the closure. I mean, it's like, as I said, like I did not write them in form, I mean, write formally, but essentially, like if you have, it's exactly like the way we saw for the alternating machine word automaton construction. So if you have x phi, then you will also have, and x phi is in closure, then phi will also be in the closure. If you have phi 1 until phi 2 in the closure, then both phi 1 as well as phi 2 will be in the closure and so on, right? It's that is there, and along with that you will also have the negations of each of the sub-formulas in this extended closure, or what we are calling now closure. Okay, so now you still see that the closure, the size of the closure is still, it's linear in the sense like it is, earlier we saw that the size of the closure was indeed linear for ABW, and here this extended closure is at most double the size of the closure than earlier closure, so it's still linear, right? So this is the thing. Now we are going to define something called elementary sets. So any question about the closure for this or the extended closure for this for the way we are defining it now? Right? Everything is fine? Okay, good. So now we are going to define the elementary sets. And what we'll say is that these elementary sets are the ones which are going to be the states of the automata. Okay, elementary sets are going to be the one which are going to be the states of the automata, which will qualify to be the states of the automata. Now it can happen that something is not reachable or something, that's a different thing, right? But these are the ones which can be the states of the automata. So let's see how we define the elementary set. So we are saying that beta, which is a subset of the closure of that given formula phi, it's elementary if it has to be consistent. It has to be consistent with respect to propositional logic, right? You know what propositional logic is, right? Yeah. So I cannot have, for example, both A and negation of A. So that is not consistent, right? So this kind of thing. Then it has to be maximal. What is meant by maximal?
You can't add something else to it.
You cannot add something further, right? The other definition of maximal is like for every formula phi, either phi is there in beta or negation of phi has to be there in beta. One of them has to be true.
Okay.
Right? Okay. So any word, if you consider any set of formulas, a formula will, a word will either satisfy phi or negation of phi. Okay? And a set of formulas, it's called maximal if either a formula psi is there or its negation is there. One of them has to be there. Okay? And at the same time, both cannot be there because that will not make it consistent. The other thing is locally consistent with respect to the until operator. Okay, which we'll see. Essentially, the idea is that like if you have phi 1 until phi 2, then either you have to have phi 2 true, or you have to have phi 1 true here, and then there should be a transition to another state, right, where you again see that phi 1 until phi 2 has to hold true.
Yeah.
Right? So that is the idea of locally consistent. Okay? So we'll just, let's see. Yeah.
So the third condition, isn't it included in the first condition itself?
No. The first condition is
Then,
with respect to the propositional logic. The third
oh,
condition is not with respect to standard propositional logic, but it's with respect to formulas like which are the temporal operators, like it's the x of phi or phi 1 until phi 2, like that.
I see. Yeah, yeah. Okay.
With respect to the temporal operators. And okay, right. So now beta is consistent with respect to propositional logic if for all phi 1 and phi 2 yeah, for all phi 1 and phi 2, and for all psi which are in the closure of phi. So phi 1 and phi 2 belonging to that beta, okay, if and only phi 1 belongs to beta and phi 2 belongs to beta. Okay, so this is consistent, and if psi belongs to beta, then negation of psi is not in beta. And it's locally consistent with respect to the until operator, that is for all phi 1 until phi 2 belonging to the closure of phi. Phi 2 belonging to beta implies that phi 1 until phi 2 belonging to beta. So note here that this phi 1 until phi 2 has to be in the closure. It's a subformula which is in the closure. Okay, it's a subformula. So if such a subformula appears in the closure, and then if phi2 belongs to beta, then the subformula phi1 until phi2, which is there in the closure, it also has to be in beta. And if phi1 until phi2 belongs to beta and phi2 does not belong to beta, then phi1 has to be in beta. Right?
Yeah.
So this is the thing. Sorry. So I think I was also I was talking about the next operator in the local consistency, but that's not quite correct. I mean, so yeah, the local consistencies with respect to the until operator only. Okay. So when we look at the transition functions in this automaton that we are going to construct, there we will see how the until and the next operator, they define the transitions. Okay. So here we are now just talking about the states first. So what are the possible states? The states are such elementary sets of form. States are such elementary sets of form. And beta is maximal if for all psi belonging to the closure, psi is if psi does not belong to beta, then negation of psi has to be beta. Okay, and this is sufficient. This one-way implication actually means the implication on both sides, right? Because you can take this as a negation, and negation of negation is the same as negation psi is the same as psi. Correct? Okay, so clear. And now let's see. Let's just try to test our understanding a bit. So suppose this is a formula given phi a until negation of a and b, a until negation of a and b. Now the closure, as we saw, it has these formulas, correct? So we already saw this. Now consider such a set, such a subset of the closure of phi, a, b and phi, a, b and phi. Now, is it elementary? Is it elementary?
It is consistent and it is also maximal.
Is it maximal? Is it maximal? So what about this one? See, this thing here, which is a subformula, either you need this or this. So neither of them is here.
Right.
Neither of them is here. Hence, it is not maximal, right? So this is not maximal. This is not maximal, right? Hence, it's not okay. What about the next one? AB, negation of A and B, phi.
That is not consistent.
This is not consistent with respect to propositional logic. Not consistent. What about this one? What about this one? What about this
It
one?
is also not consistent because we have not A and not of not A and B. So psi is not satisfied.
What I did not understand. Like you were saying, it is not consistent.
Yeah.
Uh,
I think it is consistent because not of not A and B we can think of it as A or not B. So
yeah, and you
so
have
this
the
is
not B here.
yes, I have the not B here,
Propositionally, this is
and
consistent.
yeah,
Propositional consistency is there. Right? But
No, like I mean, if we have not A and we have not of not A and B, so both these things hold true, then psi can't hold true, right?
you mean the phi here?
Half phi. Because
Okay.
it is like either A has to hold true now Sorry, either not A and B has to hold true now, or A has to hold true now.
Correct.
But neither of
Yeah.
these will.
So this is not locally consistent.
Oh,
right? I think you meant that.
Yeah.
But what it is called is it's not locally consistent with respect to the until operation. Okay. So that's the thing. With to the until operator. Yeah. Right. So all these examples, we say that they are not elementary sets. Clear? So now, if I just want to say that is the same thing, A until not A and B. So let's try to now figure out what are the elementary sets corresponding to this file. So can you now tell me what are the elementary sets? So I'll just try to write them. A, B. Then I can have, let's say, not A and B and phi.
Yeah.
So this is clearly maximal. It is consistent with respect to propositional logic. It's also locally consistent with respect to the until operator. So what about this? Negation. So okay.
Not of not A and B.
Sorry, not of you, right? So this is the one. Yeah. So this is also an elementary set. What else? Suppose I have not A, B. Okay, then I will have the not A and B. Okay, and I can have phi. This is also elementary set. I can have not A, let's say not B. Then I can have negation and B. Is it clear? Okay. So I have A or not B. Yeah. And can I have here phi? No.
Can have not.
We can have not phi. Okay. Right. So yeah. Okay. So we can. And what about this negation of?
That is same like B2, right?
That is same as, but I have not yet written the last thing. Now, what about if I write negation of phi?
That can't hold, right? Because we know phi holds because of the first three things.
What?
If
So now I'm saying that suppose if I write here negation of phi, what is wrong here? Why isn't it an elementary set? So the negation of phi, so this until thing doesn't hold.
yeah.
Yeah.
Okay, so, but that seems okay to me because this is not holding true. This is not holding true. Correct?
Yeah.
This is not holding true. This thing is holding true. Right?
Yeah.
And I'm saying that, but this first thing holding true doesn't mean that this until has to hold true forever. Right? So what does the local consistency that tell you? It tells you that if phi1 until phi2 belongs to beta and phi2 does not belong to beta, then phi1 has to be in beta.
Hmm.
But it's not the other way around.
Right.
Like if phi1 is in beta, then it's not necessary that phi1 until phi2 has to be in beta. That's not necessary, right? Because you can just have phi1 forever.
Hmm.
And that doesn't necessarily mean that phi1 until phi2 will have to go. Correct? And there can be one more, which is like A, B, and so if A and B, then I'm still having, it is not the case that A and B, and I can still have negation of phi. Right? So if I have A and B, then of course it's not true. Then not A and B is not true. So I have this. And then if I have A, B, so since I don't have negation of A and B, so of course immediately phi is not satisfied. And having just A, the first thing here doesn't necessarily mean that phi will have to go through here. Right? If I just have the phi1, if it is phi1 until phi2, if I just say I satisfy phi1, it's not necessarily that I will be satisfying phi1 until phi2, right? So this is also an elementary set, right? So we have these 6 elementary sets, right? So this is just one example. Okay, good. So now let's see how you construct, let's now try to define the automaton. So we understood what the states are. Now in the automaton, what else do we have? We will have the transitions. We will also have the alpha, like the set of good states, right? Uh, so we are going to define this automaton A5 over the alphabet, this power set of the set of atomic propositions. And what we want is that the set of words which satisfy phi, that is essentially the language of the automaton A5. And what we are going to see is that which is kind of like, once we see the construction, it should be trivial, like that A5 can be constructed in time exponential in the size of the phi, right? Why is it kind of easy to, because now the states are really sets of subformulas of phi. And how many such states you can have? Exponentially many states, right? So you can in fact construct the automaton in exponential time. And we are going to see that the number of accepting sets. So once again, we define the accepting sets. It will be clear that why such the number of accepting sets is bounded above by size which is linear in phi. Okay, so once we see the definition of alpha, so essentially it's saying that the size of alpha, right? So the number of sets in the GNBW, that is bounded above by, that's linear in size of the input formula. Okay, so here is the automaton A5. Q, then this is the alphabet, the transition function, the initial set of states, and then we have the set of accepting states, where Q is the set of all elementary sets of formulas, right? So we understand now what is meant by this elementary set of subformulas, right, in the extended closure. And Q0, which is a set of initial states. So that is also intuitively, it's clear that it's a set of all such elementary sets where the input formula phi belongs to that elementary set, right? So this is my set Q0, okay? And the alpha, there is, like, you can have many until formulas in the given formula phi. You can have many until subformulas, right, which are of the form phi1 until phi2. Now corresponding to each such phi1 until phi2, you can have a set. Okay, you can have a set, correct? So if you have, let's say, some r number of until subformulas, then you are going to have in the GNBW are such sets.
Okay.
Okay, are such sets. And the GNBW says that each of these sets has to be visited by the accepting run. Okay, if a run visits each of these sets, each of these R sets infinitely often, then the run is accepted. Right? That's what. So now, how is each such set defined? Now you have fixed such an until subformula. Corresponding to that, you have such a set of elementary sets, right? So this is the set of such beta, such that the phi1 until phi2 does not belong to the beta, or phi2 belongs to beta. Is the definition clear? It's a set of corresponding to every until formula, you get a set, right? And the alpha is again a set of such sets, right? And this one set corresponding to one until formula, which I am calling F phi1 until phi2, F subscript phi1 until phi2. This is like the set of such elementary sets where actually the phi1 until phi2 does not appear, or phi2 belongs to the phi2 belongs to that elementary set. Clear? Okay. So the intuition behind this is the following, that if you just continue to see states of the form phi1 until phi2 without seeing phi2 ever, then this is not good. Okay, this is not good.
Yeah.
Like you need to see the phi2s in order to accept the run. Okay, so that's the intuition. We'll see this more clearly. And the fact that now we have defined this alpha, now. So we can see that the size of this alpha, the size of the set alpha is at most like, or it's equal to the number of until subformulas that are appearing in the formula, right? Hence, this is the number of accepting sets, which is the size of this alpha. It is bounded above by it's linear in size of the input formula. Clear? Good. So now we are going to define the transition function. Okay, how is the transition function defined? So you have delta is of the form like you have q cross and q cross the power set of the set of atomic propositions, right? So essentially delta of q comma a, you go to a set of states, right? Like delta of q comma a, you go to a bunch of states like this, right? Delta of q comma a equal to some q1, etc., qk, like this. Okay, now each of them, you recall, this is an elementary set. Okay, now if a is not beta intersection, it's not the same as the set of atomic propositions that beta has, then delta of beta comma a equal to empty, right? You don't have any such transition. So what does it again mean? So suppose you have a state. Suppose you have a state here, and then the beta has, among other things, let's say these atomic propositions, etc. A, B are the atomic propositions, right? So now, what does it mean? It means that it can satisfy the proposition A. It can also satisfy the proposition B. So from beta, I will allow transitions which will have both A as well as B, both A and B. You recall that, like here, now the states have these subsets of the subformulas. So there can be another, let's say this beta 1, let's say there can be another beta 2 which has only A, let's say. From there, from that state, I will allow only A. That should be my, that is my, the later, that is the transition that is allowed. Clear? Okay. So if this later on which the automaton makes a transition, if it is not the same as all such atomic propositions that are there, then you have this is an this transition here is not defined. Okay. So otherwise, we have the delta of b comma a is the set of all elementary sets beta prime, such that for every xi belonging to closure of phi, we have xi belonging to beta if and only psi belongs to beta prime. Okay, is it clear? So you have such a beta now. You have another state. Suppose you have, let's say, suppose you have a beta, and let's say xi belongs to beta. So beta is again, it's an elementary set, right? It's a subset of all the subformulas of phi. Suppose you have somewhere you have x of psi. Okay. So if you have x of psi here, then on such letters, okay, on such letters, which are the set of atomic propositions exactly that are there in beta, right? On such transitions, you will go to all those states which have psi in them. All those elementary sets that have psi, you will have a transition to such uh, states. Clear? So there can be multiple states which can have psi. There can be multiple. So you will have on all of them you will have such transitions. Okay. If xi is here, then we will make transitions to all those states which have psi. Okay. And now for the for every until formula, we have phi 1 until phi 2 belonging to beta, if and only if phi 2 belongs to beta, okay, phi 2 belongs to beta, or phi 1 belongs to beta and then phi 1 until phi 2 belongs to beta prime. So you are making transitions to all such beta prime. Okay. So you have, let's say, here you have phi 1 until phi 1 until phi 2. This belongs to beta. And suppose you also have phi 1 belongs to beta, then you will make to all these states where phi 1 until phi 2 belongs to beta prime. So all such beta prime will make a transition. Clear? Okay. Okay. Good. So now in the remaining time, we'll try to prove the correctness. So let's see, it's a bit lengthy, the correctness proof, but let's see how much we can proceed. Maybe we'll be able to cover, or if not, we'll try to. We should be able to. Okay. So what is the correctness proof about? The correctness proof essentially says that this GNBW that we have constructed, right? This is essentially correct. So it accepts all those words which satisfy the formula phi. Right? The set of words corresponding to satisfying formula phi is exactly the set of is the language accepted by the automaton. So we are going to show both the directions. So one is that words of phi is a subset of L of fi. So if there is a word W which satisfies phi, then we want to show that there exists an accepting run of W in A phi. Right? So how are we going to prove this? So corresponding to every I, you look at the suffix that starting from AI, okay, and you see that what are the formulas that appear in the closure, okay, that are satisfied by this suffix, okay. So you consider, so this beta I, which is such that the set of all such formulas appearing in the closure of phi, such that the word starting from AI, the suffix starting from AI, it satisfies the psi, right? Where psi is a closure, psi is a formula appearing, sub-formula appearing in the closure of the input formula phi, right? So you consider all such psis, and the set of such psi, you consider this set, and one can see that this is indeed an elementary set, because you will only satisfy formulas, and this set should be consistent. Okay, so it corresponds to an elementary set. And now uh, uh, now what we are going to show is that this run that we are having, right? So what we get, if we do this, we are going to get subsets, right? Beta 0, beta 1, beta 2, etc. We are going to get subsets, right? And what we are going to do is that there is such a run, like this run beta 0, beta 1, beta 2, etc. First of all, this is indeed a run. So first of all, we are going to show that this is a run, and number 2 is an accepting run. Accepting run. Okay, so now one thing to note here is that the word by our assumption. So what we are showing that W belongs to this, and we are going to show that there is an accepting run. If W belongs to words of phi, so that means this word, it satisfies phi, right? And hence, by the definition of beta 0, right? By the definition of beta 0, this phi also belongs to beta 0, right? The input formula phi belongs to beta 0. Is it clear?
Yeah.
Right? So, first, so this is what we are going to show, that this is indeed an accepting run of phi. So first we'll show that this is a run, and then this run is accepting, right? So in order to show that this is a run, we have to show that for every I, from beta I to beta I plus 1, we have a valid transition. Clear? So this is what we need to first show. So suppose your formula is just a set of atomic propositions, right? Then by the definition of the automaton itself, we saw that, like, if you have the state beta, and if you have, like, if for example, if my AI is, it's a set of atomic propositions, and what you have is, like, from the state beta I, you only have transitions on AI, correct? And if that is the case, for such words, like if the formula is just, like, if I'm considering a formula psi, which is a uh, which is a which is just an atomic proposition, right? So that's an atomic proposition P belonging to AI, right? Then by the construction of the automaton, so already, like, it is indeed the case that if you have such transitions, then P, given that P indeed there is such a transition, like what I'm saying is that it is indeed the case that you have a transition, right? You have a transition from beta I to AI, where P belongs to AI, right? And you are going to beta I plus 1. Okay, so this is clear. right? So this is all I'm saying is that this is trivially true when you are considering, let's say, uh, a formula in the closure, which is just a simple proposition, right? A formula in the closure, which is just a simple proposition. For that, it's easy to see. Okay, it's trivially kind of true by the construction of the automaton itself, right? Because you are only allowing those letters such that you have like, so the AI itself is the beta I intersection this A. Okay, and the proposition is P is it belongs to that AI, and a proposition P, hence it also it's like it's there in the it appears in the set of formulas which are uh, which appear in that beta I. Okay. Now for so what are we trying to prove? Like we are trying to prove that from beta I you have like a valid transition to beta I plus 1, right? Uh, now, so if it happens that if you have, let's say, x psi belongs to the closure of phi, okay, and now we see that we say that like ai plus 1, this suffix, it satisfies x of psi if and only ai plus 1, ai plus 2, this suffix satisfies psi, and this is by induction hypothesis. Okay, what do we have by induction hypothesis? We have that psi belongs to beta I plus 1. Okay, so is it clear enough? So what we are trying to do, we are trying to say like beta I, and then we have a valid transition to beta I plus 1. Okay, now if I have, let's say, x of psi, um, so uh, so if x of psi belongs to beta I, okay, now then we are saying that we should have a transition to beta I plus 1 where there is psi belongs to beta I plus 1. Okay, the way how we have uh, how have we constructed this beta I plus 1? It's essentially the set of all such sub formulas which are satisfied by AI. Okay, like starting from ai plus 1. So this should satisfy like, so it means ai plus 1, right? By the definition of beta I, this is how we have constructed the beta I. Like it should satisfy some psi, like it's a set of such psi. If for every such, for all psi belonging to beta I, right? So this such psi's actually constitute the beta I, right? Now suppose if you say that there is an x psi belongs to beta I, that means that by the construction, by the definition of beta I, this satisfies that x of psi now, right? This, or let me not change here. So by definition, it means that this satisfies the x of psi. And by the semantics of LTL, you have, then this should satisfy psi, right? And again, by the, I mean, this is not even like, again, by the definition of beta I plus 1, you have that psi, right? So if this is satisfying psi, then psi should belong to beta I plus 1, right? And now you recall that by the definition of the automaton, okay, if you have xi belonging to beta I, then indeed there is such a transition to beta I plus 1.
Yeah.
Okay, is it clear?
Yeah.
Right? So what I'm saying that this is how I have defined the beta I's. This is how I have defined the beta I's. I have defined the automaton in some way, right? How did I define the transitions in the automaton? Like if you recall, so this was the definition. Like if I have an xi, then I should have a transition to the beta prime, which will have psi. I'll have such a transition, right? Now I'm saying that I have defined my beta I in, I have defined my beta i's in this way, right? Just by looking at like the set of formulas that I'm satisfying starting from here. Now, why is it necessary that there has to be a transition? Because I have defined my automaton using some rules and I'm defining my beta I in some way, but I have to build that connection that indeed the way I'm defining my beta I and the way I'm defining my beta I plus 1, there should indeed be a transition from beta I to beta I plus 1 in order to construct a valid run, right? So that is what we are doing, right? So now we are saying that, okay, if indeed it is the case that if I have xi belonging to beta I, then this, by the definition of beta I, this satisfies x of psi. By the semantics of LTL, this should satisfy psi. And now that means that psi, if this is the case, then indeed psi belongs to beta I plus 1. And by the construction of the automaton, right? So by the construction of the automaton, indeed there is such a transition from beta I to beta I plus 1, right? Where there is, if you have xi and if you have a psi here, then there is a transition. Okay. So for such, if xi belongs to beta I, then we have such a valid transition. Clear? And similarly, now we are also going to talk about phi 1 until phi 2, right? So we are essentially doing, like for all the different cases, like for all the different uh, kinds of like these formulas in the closure property, right? We are trying to show that we indeed have a valid transition, right? So similarly, if you have AI, let's say this is there in the uh, in your beta I. So that means again from the definition, this satisfies phi 1 until phi 2. Now, by the semantics of LTL, either this satisfies phi 2 or this satisfies phi 1 and then AI plus 1 blah blah blah, this AI plus 2, this satisfies phi 1 until phi 2. Okay. So in the first case, you have either phi 2 belongs to beta I by the definition of beta I, or phi 1 belongs to beta I and phi 1 until phi 2 belongs to beta I plus 1. And again, if you recall that the construction of the automaton, that under such case, right, we indeed have a transition from beta I to beta I plus 1, right? So this shows that this is indeed a valid run of a phi. So this is one part we did. Now what we need to do is to show that this is indeed an accepting run. This is indeed an accepting. So suppose by way of contradiction that this is not an accepting run. Okay. Suppose by way of contradiction, this is not an accepting run. So when will not this not be an accepting run? So consider that that means that there exists some until for which you are not. So every until, if you recall, that there is a corresponding accept set for every until. Okay, let me. I mean, if there is this is not an accepting run, then there is an accepting set. Let's say, let me call it some FM. Okay, corresponding to some until formula phi 1 until phi 2, such that that accept set FM is visited only finitely often. Okay, FM corresponding to FM corresponding to this corresponding to some until formula to some formula belonging to that closure of phi is visited finitely often.
So just to small out, if phi does not have any until formula in it, then
Yeah.
is there like no accepting state?
So there can be two cases. I mean, for the accept states, either there is no, I mean, so this phi 1, or maybe I can say like phi 1 j phi 2 j, in order to say that this is the jth until, jth such until sub formula, right? Or I don't know, then or maybe I can call it m, just to say that fm and phi 1 phi 2. So either this is the case that phi 1 m phi 2 phi 1 m until phi 2 m. So what is that fm again? Let's see. So let's look at the definition. So either you have the it's a set of those beta such that either that phi 1 until phi 2 does not belong to that beta, or phi 2 belongs to beta, right? So phi 2 belongs to beta. So now if I say that so it is visited finitely often. So what does it mean to say that it is visited finitely often? So you are not going to see the good states. So what are you seeing infinitely often then? So if it is seen, suppose, okay, if it is seen only finitely often, that means that there exists some I after which you stop seeing the states, some state from FM.
Yeah.
Okay. So that means for all j, let's say there is some k such that for all j greater than equal to k, we, I mean, FM does not appear anymore. Right? So what does it mean? It means that for all the states that you see, you have in those, like suppose I'm saying in all the beta j, for j greater than equal to k, in all the beta j, I have that phi 1 m until phi 2 m belongs to beta j, but phi 2 j does not belong to beta j. Right? Because I'm saying that these states are not good. Like I have stopped seeing the good states at some point. These states are no longer good. Right? So that means that all the states I'm seeing which are not good. So this is the thing. This is what I have. Clear?
Yeah.
So I can see only this. Okay. So yeah. So now what does it mean? So by the definition of the beta j's, what does it mean? That for all, so that means from the definition of beta j, all, or we can say that for all j, we have that aj plus 1, etc., they satisfy phi 1 m until phi 2 m. That is what it says in the definition of this meter j. But none of them, right? So, and it happens that, in none of them, none of the states beta j, phi to j is appearing. But it happens, and aj plus 1, etc., they don't satisfy phi 2. So for all of them, so you were saying that each of them they are satisfying this formula, but actually none of them they're actually satisfying the phi 2, right? Which gives a contradiction. Clear? Which gives a contradiction. So, right? So this is a contradiction. Clear? Okay. So what did we say? Like if you see only at some point of time, if you stop seeing the good states, then you have the until formulas there in the betas. So that means from the definition, you will like that AJs, the beta J's will not have the until formula. So the AJs that will be satisfying the phi 1 until phi 2 formulas, but none of them will actually be satisfying the phi 2j's because they are not going to, because the beta j's will not have the phi 2j, right? Because they are not good. All the beta j's will, none of them will have this phi 2j, right? So these AJs are not going to satisfy actually the phi 2j. So which gives a contradiction, right? Hence the run, we have this beta 0, beta 1, etc. is an accepting. Clear?
Yeah.
Okay. So we first proved that indeed this is a valid run, and then we proved that it is an accepting run. The run which is a valid run, it's an accepting.
Yeah.
Okay. So I will just start with the next direction. For all the cases, until this the until formula. So this is this other direction, which is the fact that the language. So we proved one direction of the construction, right? That if there is a word which satisfies the formula phi, then this word is also accepted by the automaton that we constructed.
Yeah.
Now we are going to prove the other direction, right, for the correctness. Yeah. That if the automaton accepts a word, then it indeed satisfies the formula phi. The word should indeed satisfy the formula phi. So for the other direction, suppose we consider the word W, which is there in the language. Now, you should have an accepting run corresponding to that word, since it's in the language. Suppose beta 0, beta 1, beta 2 is that. What we are going to show is that for all I, for every such subformula in the closure, if psi is in this state beta I, then ai, the suffix is going to satisfy psi. Okay. So if psi is there in that beta I, then indeed the suffix a starting from ai is going to satisfy psi.
Okay.
Right? Now we know that why this suffices, because we know that in beta 0 we have like phi belongs to beta 0. The given input formula phi belongs to beta 0. Because that's how we defined our initial states. Right? That's how we defined our initial states. And this is an accepting run starting from the initial state. Right? So if we can indeed prove that this thing, that psi belonging to beta I, it means that the suffix starting from ai indeed satisfies psi, then we are done. Okay. So for the base case, so suppose P belongs to beta I. So if P belongs to beta I, then what?
So that means that like
You can do transitions from beta I. You know that you can only do the transitions on the atomic propositions. So the letters will anyway include that that P, which we saw something similar a while ago. So it means then essentially like, so the word that the word that you are now have, that you can accept from such beta uh, from this beta I, from this state beta I. So such words should have atomic propositions which should have like a P.
yeah.
Correct? So then this is again like it's clear from the semantics of LTL and by the construction of A, the automaton A here, right? A5. We have that indeed AI plus 1, etc. It satisfies P. Right? I mean, the case of true is also like, I mean, if it is true, I mean, you can just say that everything satisfies true. So that's fine. So what about negation of phi? So suppose negation of psi belongs to beta I if and only if, oh, sorry, psi does not belong to beta I if and only if
The like AI placement and all is not satisfies.
plus 1 does not satisfy psi. This is by structural induction. This is by induction hypothesis. Yes. Oh, sorry. Okay. So this does not satisfy psi if and only if okay. So this is what we wanted to show. What about phi 1 or phi 2? It's similar again. Phi 1 or phi 2 belongs to beta I if and only if phi 1 belongs to beta I or phi 2 belongs to beta I if and only if ai plus 1, this suffix satisfies beta I, or this is again by structural induction on the formula ai plus 1, etc. satisfies sorry, right, phi 1 or this satisfies phi 2, right? So this is by the induction hypothesis. And then if and only if ai plus 1 This satisfies phi 1 or phi 2.
Hmm.
Similarly, we can also do the next, and we'll leave the final case, which is more complicated for the next lecture. So now x of psi belongs to beta I if and only if
Like AI plus 1, AI plus 2, that satisfies phi.
uh,
Okay, or this satisfies next of phi.
yeah. Mm. No, that is what we want to prove, but so x of psi is in beta I. Okay, sorry. I think you are right. So if and only if psi belongs to beta I plus 1, because this is a run. We have already said that this is a run, and the run will allow you something like x of psi, you go to another, the next state should have psi, right? By the construction of the automaton, right? So psi belongs to beta I plus 1, and if and only if by, again, the structural induction, the induction hypothesis, we have ai plus 1, ai plus 2, this satisfies psi, right? If this satisfies psi, and if and only if, so this is just from the semantics of LTL, ai plus 1, right?
Yeah.
This satisfies x of psi, right? So just say that this is semantics of LTL. Okay, clear?
Yeah.
And this if is from the definition of a phi. Let me just write in. And this if is by IH. Clear?
Yeah.
Okay. And then let's stop here, and we'll do this in the next class, and we'll finish this construction, and we'll see also some examples, and we will also try to see some lower bound of this translation, that you indeed need an exponential lower. And here, what is the size of the automaton that you construct?
Linear will be.
What is the size of the automaton that you are
Like
constructing?
for each sub formula, oh no, it's a collection of sub.
Right?
Also, 2 to the
2 to
number
the
of
size of
sub
the 2 to the size of the formula.
form.
2 raised to size of the formula,
Yeah.
right? So we have some saving. Like earlier, we were saying either 3 raised to n. If you are smarter, you may get n times 2 raised to n, because it's a very weak alternating automaton. But here it directly gives you a 2 raised to n, and we'll show a matching 2 raised to n lower bound.
Okay.
Okay, so this is this. Okay, so let me stop here. Is there any question from the online participants? Any question?
No.
No? Okay, so let me then stop the recording.